All right. Welcome, Precalculus, to another edition of distance learning. Today we're talking about parametric equations, parametric functions, basically. Then this is section 10.6. I'm just taking a piece of 10.6 though and teaching through that. It's not the whole thing. Parametric functions are a huge topic that we could spend a whole chapter or more, probably a whole unit on. Basically what a parametric equation, set of parametric equations is something like this. We've got like x equals t squared minus 4, y equals t over 2, and then we have a set of bounds on t. You don't always need the set of bounds on t, saying like what t goes from, but basically what it is you've got like your x, y coordinates, and then each x coordinate is a certain number at a given time, and the y number is a different number at that time. So basically, instead of having a function where y depends on x, we have a new function where both x and y depend on t. Now, sometimes instead of t, we could use theta as like an angle measure instead of time. But basically, when we graph something like this, what we get is we get a curve just like we're used to. It could be like a parabola, it could be a circle, it could be an ellipse, it could just be a crazy curve. There's plenty of fun ones that we'll do in the next lesson. And you'll use Desmos and that sort of fun stuff for that. But here they have direction because at a certain time, you're at a certain location. So basically what it is it's mapping a graph given where the point was at what time. So if any of you are into engineering, if you've ever used like AutoCAD, AutoCAD, like capital CAD, the computer-aided design program, a lot of that uses these parametric functions, parametric equations. It's a lot easier to do transformations with parametric functions than it is with rectangular equations, just x and y without the t in there. So there's tons and tons of uses for these. We've only got one lesson, so we're going to hit these specific learning targets, which are, given a set of parametric equations, we're going to be able to state the domain and range of the rectangular equation. So basically the domain of the rectangular equation is going to be the x's that we get, given these t's. The range is going to be the y's that we get, given these t's. We're going to be able to write the rectangular equation. In other words, if I combine these, so there's no more t, what's that equation look like? And then we're going to sketch a graph of this, including the information with t, which will give us a directed curve, which we call a plane curve. And then we'll state the key characteristics of that graph based on what we've learned in previous lessons. So let's go ahead and get started with example 1, which is right here. So here we have x is equal to t squared minus 4, y is equal to t over 2, and we have what t goes from. It goes from -2 to 3. So we want to know, for a rectangular equation, what's the domain? In other words, what x's am I going to get from this with these t values? Now you might want to think like, ooh, the smallest t value is -2, the biggest t value is 3. Maybe that's just like, just put in -2 and 3. That's not quite going to work because it's a quadratic, it's a parabola. So what we're going to do is we're going to just graph this, and we're going to look at it. So we've got t squared minus 4. So here's my t-axis, and here's my x-axis. It's kind of weird that I'm putting the x-axis vertical, but here the independent variable is t, and the dependent variable is x. So here are my inputs. And we've got 1, 2, 3 for t, and -2. Now I know when t is 0, just t squared minus 4 is a parabola with a vertex at 0, -4. Right, from what we know about parabolas, quadratics. And I know that the a value is 1, so there's no vertical stretch. So I'm just going to graph it like I graph a normal x squared or t squared. Over 1 up 1, left 1 up 1. If I go 2 away, I square that and I get 4. If I go 3 away, I'm going to go up 9, because 3 squared is 9. We got 1, 2, 3, 4, 5. So this is the curve of this part. So basically as t goes from -2 to 3, our x's go from 0 down to -4, and then up to 5. So here the domain is this, from -4 up to 5. The domain is the range of the x's, basically. So here we have -4 less than or equal to x less than or equal to 5. That's going to be the domain for a rectangular equation. In other words, when we write this just in terms of x and y, these are what the x's are going to work with. All right, let's look at the range for the rectangular equation. What we're going to do there is we're going to look at y equals t over 2. We're going to graph that. So that's just a line with a slope of 1/2. So I go 0, 0, up 1, or sorry, yeah, up 1 over 2, up 1 over 2, but I'm only going up to 3, so that's going to be at, this point here is going to be 3 comma 3 over 2. And then here I would go down 1, left 2. And we stop at -2. And that's going to be at -2 comma 1. So here, if you just put in -2 for t, -2 divided by 2 is -1. That should be a -1, my bad. And if you put in a 3 for t, you'll get 3 over 2. So here, because this is linear, you can just use these bounds, this restriction on t, to find the restriction on y. Because here is our t-axis and our y-axis. So our range is going to be from the y of -1 is less than or equal to y is less than or equal to 1/2, or 3 over 2. And the reason we're doing this is because when I put these two equations together, what I'm going to get is I'm going to get a parabola. And I need to know what part of that parabola are we graphing. And we're graphing the part of the parabola that goes here, basically. And we'll see that when we actually do this. Also, it's really useful and helpful in calculus, hopefully we'll take that next year, that you've had some of this practice with changing between variables with bounds and understanding that, like, you don't just plop them in and see where it's at. You gotta think about the function. Okay, so let's talk about finding the rectangular equation. So this is my set of parametric functions, or sorry, set of parametric equations. This blue pen, it's like not doing it for me. Let's use orange. So what I'm going to do to find the rectangular equation, the rectangular equation is just an x and y without the t's, is I'm going to solve the easiest of these two for t. I'm going to get t equals. So if I look at this and I'm going to solve that, I'd have to like add 4 and square root. We get a plus or minus square root. Not very simple. Here, I just have to multiply by 2. So I'm going to go y equals t over 2. I'm going to multiply both sides by 2. So times 2 times 2. And that gives me 2y equals t, which is this relationship, but it tells me what t is equal to instead of what y is equal to. So now I can go back into my x equation and replace the t with a 2y. So what I'm going to do is I'm going to go x equals, instead of t squared, I'm going to drop in 2y squared minus 4, because that's what t is equal to. Now I can simplify this. We've got to remember our exponent rules. So x equals, well, 2 squared is 4, and then y squared minus 4. So the rectangular equation is x equals 4y squared minus 4. If you wanted to, you could add the 4 over and then divide by 4, get it in that standard form equation. This is fine though. So x equals, well, let's actually factor the 4 out. Let's go like this. 4 times y squared minus 1. Let's not do that. Let's not do that. Nope, we're not doing that. So 4y squared minus 4. There we go. That's the rectangular equation. Or we could go like add the 4 over, x plus 4 equals, and divide by 4, so 1/4, x plus 4 equals y squared. Right, you see we've got a a vertex at negative 4, 0, and right, we've got a 1/4, so like 1/16 would be our p-value. Don't worry about that right now. Let's look at, this is fine for the equation for a parabola. That works. So here, let's look at the graph. Now, for a parabola, let's see, how would we want to graph this? Yeah, let's graph it this way. We can graph it here knowing that the vertex is at negative 4, 0. Let's get a different pen out. Actually, sorry. I didn't quite prepare well enough for this, so I'm apologizing for that now. Hang with me though. So I'm taking a step back. We know the domain for this graph is going to be between negative 4 and 5. So I'm going to go 1, 2, 3, 4, negative 4, 1, 2, 3, 4, 5. All right, I know the range is between negative 1 and 1.5. So I'm just going to go like negative 1, so it's like negative 1/2. 1, 2, so it's like 1/2, 1/2, 3/2. Excuse me. So what I'm going to do here is I'm going to use the fact that negative 4, or sorry, hang with me. I'm going to find where this starts. In other words, when t is negative 2, what's going on here? And what that's going to do is going to tell me the starting point, and it'll give me the direction of this plane curve. So if I put negative 2 in for t squared, it's negative 2, I get 4 squared minus 4 is 0. So I'll make a little table here where I have t, x, and y. So when t is negative 2, x is 0, and y is 0. Oh, nope, sorry. There, I'm putting, it's t is negative 2. So I get negative 2 divided by 2 is negative 1. Okay, when t is negative 1, I'm going to get 1 squared, negative 3 for my x, and then I'm going to get negative 1/2 here. All right, I'm going to go 0, 1, 2, 3. We're just going to plot out what this looks like, and then that's going to give us an idea of the direction that this curve is going and kind of how it goes, like how fast it goes as well. All right, so if I put in 0, 0 squared minus 4 is negative 4. 0/2 is 0. If I put in 1 squared minus 4 is negative 3 again. Oh, that doesn't go there. Sorry. Yikes. If I put 1 in here, I get positive 1/2. If I put 2 in, 2 squared minus 4 is 0. And then 2/2 is 1. 3 squared is 9. 9 minus 4 is 5. And then 3/2 is, well, 3/2. So what I'm going to do now is I'm going to graph each of these points. I'm going to plot it out. So I have 0, negative 1. That's right here. That's my starting point for this plane curve. And then as I go to negative 1, I go to negative 3, 1/2. And then I have negative 4, 0 is my next point, right? So that's my x and y coordinates. Then I have negative 3, 1/2, negative 3, 1/2. And then I have 0, positive 1. And then I have 5 and 3/2. So here I get this curve, which is a horizontal parabola, like I said earlier, correctly, surprisingly. The vertex is at negative 4, 0, right, from this. And what's happening here is we have direction now. Because t starts here at negative 2, this is when t equals negative 2, this is when t equals 3, we don't just get this horizontal parabola shape, we get this traveling along it. That extra t parameter gives us that direction arrow. If this was negative 2 for t up here and this was 3, then the arrows would be going the other direction. Okay. All right, and then key characteristics, right? We could go about and be like, all right, vertex is at -4, 0. And then the directrix, right, is going to be right here. With this, the p-value is going to be, 4p is 1/4, so it's going to be 1/16. Because 4p equals 1/4, we divide by 4, right? You get 1/16. So it's going to be -4 minus 1/16, 0. Nope, that's a mistake a lot of you made on the last one. Oh my goodness. Sorry, it's going to be x equals -4 1/16. So x equals -4 minus 1/16. And then the focus is -4 plus 1/16, 0. Sorry about that. Woo! I promise the other problems will go better than this one if you're still actually watching. Okay, so that's the first example that goes similar to problem 1 on your assignment. Yeah, hopefully that made some sort of sense. Basically what you do is identify domain and range by looking at the graphs of these with this domain where x and y are the outputs on each of these graphs. That gives you your domain and range. Rectangular equation, solve one of these for t so it gets t equals, and then substitute it into the other equation. So here we said 2y equals t, replace, right? Simplify, rewrite it. If you want to, you don't have to. For the next ones, you will. And then sketch the graph. You can use this to graph it, or you can use this to graph it. Just make sure you identify the direction that you go in. And focus would be right there. Okay, so I'm going to go to the next problem. So the next problem we're going to have is going to have a parameter of theta instead of t. So basically it's an angle measure that's changing instead of time that's changing. They can be interchangeable. It doesn't really matter which one goes with which. All right. Just got to erase this off. Okay. Let's make this one a little bit better, a little more smooth. Sorry, for some reason I'm just off right now. We'll get it. I know it's a video and I could just start over, but I'm stubborn. All right, so we got, let's use orange. X equals 3 cosine theta plus 2, and y equals 4 sine theta minus 3. And we have 0 less than or equal to theta is less than 2 pi. So this is where it gets fun. That other one, not that much fun. This one is much more fun. So first thing we're going to do is we're going to find the domain and range. So domain and range of the rectangular equation. So for the domain, I'm going to look at this. Basically, I'm going to look at the range of this first one with the x, because domain in general is represented by the x. But here, the independent variable is the theta, and x depends on theta. So in order to get my rectangular, we got x depending on y. I got to figure out what x's I get. So I'm just going to look and say, all right, how do I graph this for from 0 to 2 pi? So we draw our little theta down here, x up here. It's a cosine function, so we have a midline at 2. We have an amplitude of 3, so 1, 2, 3. 1, 2, 3. So this is at 5, this is at -1. And there's no phase shift, and it doesn't have a horizontal. Oh my goodness. Horizontal stretch or shrink. Dilation doesn't have one of those. So we can just go like pi over 2, pi, 3 pi over 2, and 2 pi. All right, so cosine starts with maximum, goes maximum, midline, minimum, midline, maximum, right? The graph would look like that from 0 to 2 pi, which tells us we get all of those x's. So our x's are going to be from -1 less than or equal to x is less than or equal to 5. So we go from -1 to 5 for our x's, right? This would be an opened up, but we get that there. Sorry, we get the 5 here when when theta is 0. So to find our range, what we're going to do is we're going to sketch out the sine function graph. So here it's a -3, 1, 2, 3, -3 for our midline, 1, 2, 3, 4, right? Because we have 4 for our amplitude, 1, 2, 3, 4. So that's at 1. And once again, right, break it into quarters, right, pi, 2 pi, pi over 2, 3 pi over 2. Start at the midline, sine starts at the midline, goes up, midline, minimum midline. We get a function that looks like that. And once again, sorry, we'd have an open circle there. We get all the y numbers, right, because this is theta, and that's y. We get all the y numbers from -7 up to +1. So -7 less than or equal to y less than or equal to 1. Wonderful. Cool. So we have the domain and range. Now what we're going to do is we're going to find the rectangular equation. This is fun. If you don't think that's fun, well, hopefully you'll think this is fun. So rectangular equation. The reason it's called a rectangular equation is because it's just in terms of x and y make a rectangular coordinate system where you go right or left how much, up or down how much, to make like every point basically makes a rectangle from 0, 0. So this is the tricky part. We look at this, we're like, if I gotta solve that for theta, you're like -2 divided by 3 and then take cosine inverse? Yikes, then I'd have like a 4 sine of cosine inverse of stuff with an x -3. No thanks. How would we? What we're gonna do is we're gonna think back to what we know about the relationship between sine and cosine. And we know this lovely Pythagorean identity that tells us if we have sine squared theta plus cosine squared theta, that equals 1. So essentially what we're going to do is I'm going to say, well, can I make this equal sine squared and make that equal cosine squared? And then I could have something plus something equals 1. So I'm going to solve this. So solve for cosine squared theta. Or sorry, I'm just going to solve for cosine theta. I'm going to solve for sine theta here. So let's get a different pen. Let's go pink. Here I have x equals 3 cosine theta plus 2. I'm going to subtract 2. X minus 2 equals 3 cosine theta and divide by 3. So I have x minus 2 all over 3 equals cosine theta. Now I'm going to solve for just sine theta, get sine theta by itself. So I have y equals 4 sine theta minus 3. I'm going to add the 3 over y plus 3 equals 4 sine theta. Divide by the 4. So I get y plus 3 over 4 equals sine theta. Lovely. We've got a cosine theta and a sine theta. What we want is a cosine squared and a sine squared. So what we're going to do is we're just going to square both sides of each equation. So here, I'm going to square the cosine theta. I'm going to square the 3, and I'm just going to square the x minus 2. So here, I'm going to square the y plus 3. I'm going to square the 4, and I'm going to square the sine squared. So now what I can do is I can replace cosine squared with x minus 2 squared over 9, because 3 squared is 9. So I'm going to get x minus 2 squared over 9 plus sine squared, because this is cosine squared, plus sine squared, right, equals 1. So here I get y plus 3 squared over 4 squared is 16 equals 1. And that is the rectangular equation. And we're like, hey, that looks familiar, right? It does. So this is the equation for, you say it, and I'll confirm it, for an ellipse. Yeah, right? Because it's squared plus squared equals 1. Different denominators, right? If this was a 9 and that was a 9, we would multiply everything by 9 to make that, right, equals 9. So it'd be a circle if they had the same denominator. They don't. So here it's going to be an ellipse with a vertical major axis. So let's go ahead and graph it and go from there. So, and this tells us here that since theta goes from 0 to 2 pi and these are regular thetas, we're going to get the full rotation of the circle. Oh, ellipse, not circle. Sorry, misspoke. So here, right, we've got the key characteristics as well. Right, we can say what the center is by looking at it. Center is going to be at 2, -3. We can say where the vertices are, right, vertices. Oop, I put an extra little thing in there. So the vertices are going to be up and down because the 4 is underneath. So it's going to be 2, 1 and 2, -7. Check it out. That matches up with our range. The co-vertices are going to be left and right 3. And the Emma bear! Yeah! Hi, Emma. Hi, Emma. Oh, she's the squirrely one. Hi. Okay, so the co-vertices are going to be 3 right or left from the center. So that 2 is going to go +3 -3. That's going to give us our -1 or +5 from our domain. So we get -1, -3, and we get 5, -3. And then we can grab the foci later in a moment. So 2, -3, just sketch this graph. 1, 2, 1, 2, 3. There's our center. Vertices are here and here. Co-vertices there and there. Sketch it in. Right, for the foci, for an ellipse, remember it's 16, or sorry, c squared equals a squared minus b squared. So 16 minus 9 is going to give us 7. So c equals square root of 7. So we're just going to go up or down square root of 7, which is a little under 3. So 1, 2, 3, boop. There, 1, 2, 3, there. So the foci are going to be at 2, -3 plus root 7 and 2, -3 minus root 7. Okay, cool. I think that's it for that one. We got all the info that we needed. The last thing we need is the direction arrows on this graph. So what we're going to do is we're going to say at 0, right, where are we? Our x is at 5 and our y is at -3. So 5, -3, that's the starting point. And then let's say we go to pi over 2. So when we go to pi over 2, we're at an x here at 2. So x equals 2. And here y equals 1. So 2, 1 is right there, which tells us our graph is going counterclockwise, just like a unit circle angle would. All right, and that's the last part. Don't forget about that for a parametric equation. Sorry, for when you're graphing a set of parametric equations, to remember to include those arrows to tell you what direction that thing is going. Sorry, that function. All right, one more for this video. And then that'll be it. I'll make another video with a couple more examples, just because, well, if this didn't work for you, then there will be some more stuff for you to work through. And if you've made it this far, good work. All right. So the next one, another fun problem, much more fun than the first one, is we've got x equals 1 plus 3 secant theta. So x equals 1 plus 3 secant theta. And y equals -3 plus tan theta. And theta is going to go from pi over 2 less than or equal to theta less than or equal to 3 pi over 2. And we have the same set of things that we need to do. We define the domain and range of the rectangular equations. Sorry, domain and range of the rectangular equation. We are going to write the rectangular form equation from those. We're going to put them together, see what we get. We're going to sketch the graph using both pieces of information. What we know about the rectangular one, what the graph should look like, use the parametric functions to draw the direction arrows on it, and then we're going to identify key characteristics of the graph because it's going to look like something we're familiar with. So what I'm going to do is I'm going to find the domain and range first. So the domain is going to be basically looking at this, which is x equals 1 plus 3 secant theta. And remember, secant theta is 1 over cosine theta. So if I'm going to graph that, which is what we want to do, is this is going to be theta and this is going to be x. So the outputs here are my x numbers. Okay, so 0, pi over 2, pi, 2 pi, pi over 2, 3 pi over 2. We got a midline of 1, 1, 2, 3, 1, 2, 3. So this is negative 2, this is at 4. And if I'm going to graph in my cosine function, right, it would look like this. Here, 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 here. Right, remember we do it just with dash because we're looking at secant. So when I'm looking at the secant function, what I do is I say, oh, everywhere that cosine hits its midline is going to be an asymptote. So I draw in my asymptotes here. So we notice, oh, look, those asymptotes are between those asymptotes is on the left, it's pi over 2, on the right is 3 pi over 2. So really I only care about this part of the graph for my thetas. So what I'm getting is from negative 2 down. So here, the domain is all the x's that are less than or equal to negative 2. So basically when I graph my xy rectangular graph, I'm just going to have, here's y, here's x is negative 2, only on that side. All right, so now let's look at the range. So here I'm going to look at the y equals negative 3 plus tan theta. So I got to graph a tangent function here within the same bounds. So remember tangent, we got pi over 2, pi, 3 pi over 2, 2 pi, negative pi over 2.